Well, today we're continuing with lesson 4-6. It's called Isosceles and Equilateral Triangles. Hopefully you've heard those words before. Here's some general information in case you don't remember, and actually there's some specifics in this lesson that are important to overlook. So if you look at this first portion in your lesson in your book, and I am on page 285, if you want to look in your book. It goes through a great explanation of the, I guess, anatomy, if you want to call it that, of a isosceles triangle. I think you've been taught in the past that isosceles triangles have at least two congruent sides, which is true, but you may have never been told that there are certain parts of the isosceles triangle that have names. And in this one that's drawn here, angle 1 is, which is right here, this would be called your vertex angle, okay? Because the definition of a vertex angle, if you look up here in the wording, it says that it's the angle that it's the angle with sides that are the legs. Well, what are the legs of an isosceles triangle? We'll look up above that. It says the legs of the isosceles triangle are the two congruent sides. And so basically they always come, the two congruent sides always come out of the vertex angle. And so that means that this leg and this leg are going to be congruent. And then they have another set of vocabulary about the angles, and these are called base angles, okay? Angles 2 and 3. So this top one's called a vertex angle, but the bottom ones are called base angles, okay? And it's real important to understand what each thing's called. And so then this bottom side here is called a base. Now, obviously this triangle could be turned upside down. For instance, if you look in Theorem 410, this isosceles triangle is turned upside down. So this is the base, this is a leg, this is a leg, this is your vertex angle, and then these two angles here, A and B, are called your base angles, okay? So no matter which way they turn this around, you should be able to identify that the vertex is the angle that the legs are basically, the legs make up the sides of that angle. And then the base angles are opposite of the base angles. So if you're like, what does that mean? Well, let me erase all this and I'll kind of use some arrows to point this out. In this upside down one, if you look here, across from angle A, which is a base angle, is that opposite leg right there. And then across from base angle B is that leg across from there. So your base angles are always congruent. And so let's go over these two isosceles triangle theorems, 410 and 411. 410 says if two sides of a triangle are congruent, then the angles opposite those sides are congruent. So it's basically saying that the base angles are congruent. And then conversely, if two angles of a triangle are congruent, then the sides opposite those angles are congruent. So that's what 411 is showing you, is that if they show D and F are congruent, that means this leg and this leg are congruent to each other also, okay? It goes both ways. 410 is the opposite. It says if two sides of an angle are congruent. So let me erase that so you can actually see. You see the sides are congruent. So because of that, we can say then that angle 2 is congruent to angle 1. The base angles are congruent. So commit that to memory. It's a real important couple theorems to know. Then also we've got some theorems about equilateral triangles. Equilateral triangles are triangles that have 3 congruent sides. So here's something to think about. All equilateral triangles are isosceles triangles, but not all isosceles triangles are equilateral triangles. So think about that in your head. All equilateral triangles are isosceles triangles, but not all isosceles triangles are equilateral triangles. And that's because equilateral triangles have 3 sides that are congruent. Isosceles triangles have at least 2 sides congruent. So that's why equilateral triangles are also isosceles triangles by definition. But equilateral is the best way to identify a triangle with 3 congruent sides or 3 congruent angles. Okay, so let's look at corollary 4.3. So the isosceles triangle theorem leads to 2 corollaries, which we're about to talk about the angles of an equilateral triangle. And here it says, if A, B, and C angles are congruent, then all the opposite sides are congruent. So that's basically like I say, an extension of what happens with isosceles triangles. The 4.4 corollary says, each angle of an equilateral triangle measures 60 degrees, okay? And that's true because the triangle sum theorem tells us that all 3 angles have to add up to 180. So if they're going to all be the same size, you divide that evenly by 3 parts, or by 3, you're going to get 60 degrees each, okay? So those are some important corollaries to know. So let's just dive into some problems. I'm going to do 1 through 7 with you. Then I'm going to give you some hints on the ones you're going to be trying on your own. So let's start with number 1. If AB is congruent to CB, you know I'm a huge proponent of marking what they tell you, okay? Name 2 congruent angles. All right, so basically from that information number 1, we know these 2 sides are congruent. Those 2 sides with this side form an isosceles triangle. So from our definition of isosceles triangle, we know the base angles are congruent. So we can say this angle and this angle are congruent to each other because those are opposite those legs. I really don't care about that smaller triangle at all because they only told me something about the larger triangle sides, okay? So we're just going to kind of pretend that smaller angle inside there's not even present. So our answer for this is simply going to be the 2 congruent angles, which I'm going to name angle BAC and angle BCA. And I should have put a little angle measure. Okay, so I'm going to clean up our diagram here. All right, so now we're going to go on to number 2. Number 2 says, if angle EAC, so again, you know how I like to mark things, angle EAC is congruent to ECA. So that means this little angle here and this little angle here are congruent to each other. So they said name 2 congruent segments. So we know that if we have 2 angles that are congruent, the opposite sides of those angles are congruent. So therefore, and again, that's because of the first 2 theorems I went over with you. So if you don't remember that, go back to the beginning of the video. Those are the first 2 I covered. We did the we did the original theorem and then the converse of it that described that. So listen to that, look at the figures a little bit more carefully if you aren't sure what's going on here. So EA is congruent to EC. They just want us to list the 2, so we did that. Okay, let's skip on down here to number 3. Number 3 says they want you to find each measure, and right here it says they want us to find FH. So, from the triangle, we only know something about this side right there. That's not FH, that's GH. But look what else they give us. We know these 2 angles are 60, and we know by default this has to be 60 because all 3 have to add up to 180. Well, that tells us that this must be an equilateral triangle because if you look back at the corollaries that I went over just a minute ago on equilateral triangles, it says if angles AB, or in this case it's F, G, and H, if those 3 angles are congruent to each other, then all the sides are congruent to each other. And again, look at corollary 4.3 for that specific information. So I'll write corollary 4.3. So if you don't understand it, it's very important to go back and read that corollary, look at what it has in the example, look at the picture, and study that for a little bit, okay? All right, so then we know that's true. According to corollary 4.3, that means all of these are congruent. So therefore, FH is 12. And it's also very important in geometry to always look back at what allows you to say that. Don't just say it because, oh, you think that's right, or you seem to remember something. Know exactly what corollary or what theorem or what postulate it says it in, okay? That'll just help you on future problems figure stuff out that maybe not be obvious at the beginning if you just make that a habit on the easier stuff. Okay, so this one they want us to find angle MRP. So MRP is this angle right there. Well, if you look back at corollary 4.4, it says, and again that's on page 286, each angle of an equilateral triangle measures 60 degrees. Okay, well, we know this is an equilateral triangle because we have 3 congruent sides marked here. So again, if you read 4.4, it clearly says each angle of an equilateral triangle measures 60 degrees. So it says, in the example there, it says if the 3 sides are congruent, then the angles are equal to each other. And so if they're equal to each other, they got to be 60 for that to happen, right? Because 180 divided by 3 equals 60, okay? So our answer for angle MRP is 60 degrees. Okay, let's move on to 5. 5, the directions say find the value of each variable. So in number 5, we have a z that we need to find. And from this, we kind of have a equilateral triangle that's kind of tilted on its side a little bit. This is our base. These are our base angles. And how I know that is because they're the ones side by side, and they're congruent. And we learned on page 285. So again, if you're lost, look back at 285. It says if you have 2 angles of a triangle are congruent, then the sides opposite those angles are congruent. Well, that's going to help us because that tells us that this SR side is congruent to this RT side. And again, that's because of the theorem on page 285, specifically 4.11, okay? And so after we look at that, we're able to say, okay, well, since we know those angles are congruent, then we know those sides opposite are congruent. So therefore, we know SR is congruent because of this page 285, theorem 411. We know SR is congruent to RT. What do we know about SR and RT? Well, segment SR is equal to, so I'm going to just do some substitution here. And I'm going to erase this little base angle description here so I have some room here. So I know SR is 2z minus 15. I know RT is 9. So once I find what z is, I'm actually done because it just said in the directions to find the value of each variable. But I already know, another way to look at this is both of these sides are equal to 9 ultimately because they are congruent to each other. So that's another way to think about it too, rather than doing this substitution thing. But I tend to do figure out my equation I'm going to use and substitute my expressions and solve. I can tend to use that process over and over because it's reliable to do it that way every time. All right, so that's 24, and we do our math, and we're going to get z is equal to 12, okay, on that one. Let's hop on over to 6. This one's a little different. It's talking about angles. Let's see what we've got here. Well, We know that we've got an isosceles triangle because here's a side with 8 and here's a side with 8. And because of that, we know these base angles here are going to be congruent. Well, I don't know what this angle y is, except it says it's 4x minus 2, but actually I know it's 62 degrees. But they're not asking us what angle y is. They're asking us what x is. So I'm just going to say that I know angle x is congruent to angle y, and the reason, again, if you look back at page 285, and I'll write this over to the side, it says if you have two sides that are congruent, then the angles opposite them are congruent. That's theorem 410, okay? And so that's why I can say angle x is congruent to angle y, because of theorem 410. So now I'm going to substitute. Angle x is 62. Angle y is 4x minus 2 degrees. So I'm just going to add 2 to both sides because I need to figure out what x is. And then when I solve for x by dividing by 4 on both sides, 4 into 64 is 16, okay? Again, if they asked me for angle y was, that would have been the easy thing. I could have just said 62 and not degrees, and I had to solve it all. But they want us to go a little further with that. All right, so let's move on to a proof. I'm going to do like I always do, mark up the diagram if needed. Sometimes they tell us everything on the diagram and sometimes they don't. They tell us that ABC is isosceles. So even if they did not mark the diagram, the fact that they told me ABC is isosceles actually tells me, and B is always the middle letter. If it tells you an isosceles, that is your vertex angle. So I want to point that out. That's one reason I liked this proof, because so I know that means that since this is the vertex angle, angle B, and I know the legs come out of the vertex angle, I know these are congruent. So I really didn't need them to tell me that. I just knew that because they told me it was isosceles, that triangle ABC was isosceles. But they do tell us something they did not mark. They say that EB, segment EB here, that's going kind of down inside this triangle, bisects angle ABC. So that tells me that BE cuts this angle ABC in half. And then if you look at this, what we're trying to prove, it says, prove that triangle ABE is congruent to CBE. Well, that's not going to be too hard because those two, we're just trying to prove that these two triangles that share a common side BE are congruent to each other. Well, we know that they both have the same side BE for both of these triangles. So basically, just from the diagram, we can tell that, I'm going to go erase these since we don't need them. It's already marked. Makes it a little cleaner. We already know what theorem we're going to use. Hopefully you know what theorem you're going to use to prove that these two triangles are congruent. We're going to use side, angle, side, because we've got side, angle, side. On both triangles we have congruent, we've got two congruent pairs of sides and one congruent pair of angles, and therefore we can just have, that's just enough information to prove these triangles are congruent. So now all we got to do is just put this in written form, okay? So what I'm going to do is, I don't want to squish this in. What I'm going to do is I'm going to come down here to a new page where I can find some blank pieces here. Here we go. And I'm just going to write it, okay? So here's your proof. And I'm just going to switch to blue. Okay, so this is for number 7. So, statement, reason. The first is always the given, so I'll go ahead and fill that in. Okay, so the first step is just reiterating what they already told us. ABC is isosceles. EB bisects angle ABC. B, C, okay? So that's all in our given. Next, we know that AB, you'll have to look back up at the book, but we knew AB is congruent to BC. Now, as I mentioned earlier, I know they gave it to us in the picture, and I kind of wish they didn't, because then it's a little hard to tell what you're supposed to write. But we know that AB is congruent to BC because that's the definition of isosceles. They tell us that this is an isosceles triangle to begin with, so therefore we know those sides are congruent because those are the sides coming out of angle B. And so just keep that in mind. All right, step 3. So that's got our pair of sides taken care of, all right? We got one pair of sides. So I'm putting a little S for the SAS that we're going to be doing, okay? Just to kind of keep track, make sure we got everything. Just to go in order of SAS, I'm going to identify my two angles that are congruent to each other. And we figured out that angle ABE is congruent to angle CBE because we know what an angle bisector does. So definition of angle bisector. It's just simply, they told us that BE, and if you look back in the given, it says EB bisects ABC. So therefore, we know those two angles are congruent to each other because we know what bisects means, okay? When something bisects an angle, it creates two congruent angles. So that's all we have to put for reasons. I'm going to put a little A right here. Just say, okay, we got the S and the A done. Now we got to confirm a third side in each triangle that's congruent. And that is BE itself. BE is congruent to BE, and that is our third side for both of our triangles. They share the same. So again, when we're just stating something is equal to itself, we're just establishing that BE is one and the same. It's not like there's these two separate segments that are different lengths and they're both called BE. We're saying that they are the same length. So it really doesn't matter if this triangle is sharing a side or it was separated and somehow they told us that BE was congruent, but we can tell just from the picture it is because they share the same side. That's what made it so easy. So we got reflexive, property, and so we've got the S, the A, and the S done. So we're actually done with the proof. We can actually put down what we're trying to prove, which was ABE is congruent to triangle CBE. And again, our reasoning was because we proved two pairs of sides and one pair of angles between the two triangles were congruent, so we are done with that proof. So with proofs, always try to, be doing these on your own ahead of me, and then if you can't, if you get stumped and need to look, that's fine. But then maybe go back to it again and see if you can do it yourself, okay? So I'm going to give you a few hints here and there on anything that might look a little confusing. So in the work you're going to do on your own, this little section right here, we've got 11, 13 in this section that I've assigned to you. Basically, this one can be a little confusing because you've got a lot of figures going on here. But like I said, in the one I did with you, just focus on the part it's talking about for that particular problem. So for like number 11, it says CA is congruent to DA and name two congruent angles. So all you're caring about is this triangle right here. Nothing else matters. So in that triangle there, you're naming what are the congruent angles, okay? And again, if you're confused, look back at your theorems that I first told you about on page 285, okay? And then number 13, a little hint here. It says BCF, angle BCF is congruent to BFC and name two congruent segments. So BCF, let me erase this. So if you're looking at BCF, that's going to be this angle. And then BFC is this angle, okay? So you're only looking at this triangle, okay? So I've just basically, those are congruent to each other, so those are your base angles, so you name the two congruent segments, okay? So just want to give you a little hint on those. And then moving on down to the next page, we're down at 15. This one, they want you to find angle BAC. Okay. Now I'm going to give you a little hint on this. They want you to find this angle. Well, you know that since these are congruent, these are your congruent base angles, and you're trying to find this one, all right? Well, we don't know what angle C is, so it's a little hard to tell what angle A is, but this is key right here. If you've got 180 degrees in a triangle, okay, then 60 is used. You got 120 left. Well, the 120 has to be split evenly between the base angles because they got to be the same. So there's your hint there. And then 17, they want you to find TR, okay. Well, again, we know this is a isosceles triangle because they're both 4 in length. And so if that's true, then these got to be congruent. So it's kind of a similar situation here. We know that since this is 60, what's left is 120, and they have to be equal, so they all got to be 60. And so from that, we know this is an equilateral triangle, so you should be able to figure out what length the TR is, because they told us what these were, okay? So you know it's an equilateral triangle, so go from there. And then on down to 19. This one we know is an equilateral triangle. So if that's true, then we know something about these, right? So you can set up them equal to each other and solve for x, and you just have to find the value of each variable. So that's all you got to do. So all you got to do is set them equal to each other, okay? And then 21 is, let me see if I can get it all in here. Okay, so we know here's our congruent legs. So therefore we know these are congruent to each other. Those are our base angles. And the thing that's a little confusing here is that your angle X and your angle Y, okay, have two different variables in their expressions. So we're going to have to think a little bit through that, but actually this is very similar to the other one we've just done. If this is 52 degrees, we can subtract 52 and figure out what that amount is, right? Which should be 128, okay? Well, we know 128 degrees is left, and we know that has to be split between angle X and Y evenly, so we divide that by 2. We get 64. So now we know that angle Y is 64 degrees and angle X is 64 degrees. So therefore, we can set 4x plus 20 equal to 64 and solve for X, and then set 6y minus 2 equal to 64 and solve for y, okay? So basically we found the angle measures, and that will help us find our x and y. Okay, so there's your hint for that. And moving on to 29, we have a figure over here. 29, they want you to find the measurement of angle CAD, which would be this angle right there, okay? And so since we know this is 92, we know these two angles here and here are going to be the same because our isosceles, now they didn't draw it to scale. Those do not, even though they're marked congruent, they don't look it. But we do know that these two angles here at the opposite this 90 degrees are equal to each other. So if 180 minus 92 equals 88, then we simply know that we're just going to divide that 88 by 2, and that will give us each of our angles, A and C. Now we only need A, okay, because A is the middle letter there. So if we divide by 2, that will get us our answer, okay? And then the next one is 31. And again, if I go too fast, just rewind me so that you can get it the speed you need, okay? And then ACB is this one right here, okay? Well, just a minute ago, I wanted to go and say this because we kind of need it for this next one, okay? They want us to find this angle right here, all right, ACB. So now we know that this is a linear pair, so we can just simply, and they're adjacent to each other, so we can just do 180 minus 44, and that will help us figure out that missing angle there for 31. And then last but not least, I'm going to give you a little helpful hint on 39. And this one's kind of a doozy. All right, let's see if I can get enough space here. They want us to find y, because it says in the directions it says find the value of the variable. So for number 39, I definitely I want you to try it on your own, and maybe just at least set up the problem. And then the math part of it you might be a little confused about because you probably have not worked with quadratics in a while. But here's what we know is true. We know that this is an isosceles triangle, so these two are equal, right? So therefore we know that this is also equal to 2y minus 5, okay? And so hopefully from here you realize that this angle plus this angle plus this angle equals 180. That's really all we know. So we can write that up here. It's going to be kind of ugly, but it's the truth. And I know some people will probably write 4y minus 10 to begin with. They'll just go and combine those. I just wrote it out so that we clearly see it's this angle plus this angle plus this angle equals 180. And so now we're going to combine like terms. So I only have one y squared term. I have a 4y that I can combine. I can combine these two. And then I can combine the negative 5, the negative 5, and the negative 62. That's going to be negative 72. Okay, so for those of you who may be a little shaky on quadratic, you may not realize this is a quadratic equation. And so that means you could have two possible answers, and they could be a positive and a negative answer. And whatever answers you get, you could have one or two answers, but for geometry you have to make sure that both answers make sense because we're measuring angles, so we're not going to have negative angle measures, so just be mindful of that. But the first thing we're going to do to make this look like quadratic form, and this is what quadratic form of equation looks like. It doesn't quite look like that because we don't have a 0 right there. So what we need to do is subtract 180 from both sides, and that will give us our 0 we need. So I'm going to add 180 to both sides, and what that's going to do is that's going to give me, I'm sorry, I meant to say subtract 180. I can't remember what I just said. But if I subtract 180 from 72, negative 72, that's like adding two negative numbers, right? So I'm going to get a negative 252. All right. Now, at this point, you're probably like, how in the world do I solve for y? There's two ways you can do by factoring, okay? And what you do with that is you think of two numbers that will multiply to give you a negative 252, but add together to give you a 4y, okay? So be thinking of those numbers on your own and pause this video, okay? And then when you unpause it, I'll reveal what the two numbers are. Okay, so if you kept working with it, you'd realize that 18 times 14, or specifically negative 18 times positive 14, will give you a negative 252, okay? But added together will give you a negative 4, and that works because if you look back over here at our equation, oops, I had that backwards. I needed it. Remembered it wrong, I guess. Okay, we needed a positive 4. So that means it would have to be this way. We need a positive 4, excuse me. I realized that when I went back to the equation. So in order to get that to work, an 18 times negative 14 gives me a negative 252, but added together they give me a positive 4. So that fits my criteria of me needing a positive 4 and a negative 252. So then you put it in factor form, which we're using y, so that means I'm going to put a plus 18 and a y minus 14. This is kind of like, if you remember foiling, which is a fancy word for distribution. If I were to FOIL these factors, I would get this equation right here back out if I do this correctly, okay? And so y times y is y squared. And then that would be my first. My outer would be y times negative 14 was negative 14y. My inner is positive 18y. And then my last would be 18 and negative 14 multiplied together. That would give me negative 252. And so when I simplify terms and everything, I would get what's circled in red over here back out of it, so I know I did it right. Okay, so now here's where my answers come in. So in order to finish this out, I would get y plus 18 equal to 0 and solve for y, and I'd subtract 18 on both sides and get negative 18. And then the second one, I'll continue up here, was y minus 14. Set that equal to 0, and I'll realize my answer will be 14. So I've got two answers. I've got y equals 14 and y equals negative 18. Now the negative 18 does not make sense because if I plug negative 18, for instance, into this angle expression here, I'd end up with a negative angle measure, and that's impossible in a triangle. So in this case, this is the only one that would make sense, so that's the only answer. All right, well, hopefully the hints I gave you on the others will help you figure that out, and this last one was a doozy. So try it on your own and see how you do with it. Bye now.